Okay, so last couple of classes for the semester. So in today's class, we'll wrap up our example about inter-process communication. You're looking at how do you create a pipe, and then how do you communicate between two processes. We started talking about this example, but we didn't really go into it. So we'll try to finish this up first, and then we'll get into CPU scheduling algorithms. We'll talk about need for a scheduler, what are the different scheduling algorithms that are commonly used in operating systems. And then, depending on how much time we have left, we may or may not get into the next lecture about deadlock. The scheduling, CPU scheduling topic is pretty straightforward, so I'm assuming that we are going to breeze through that. So let's see how much time we have left at the end. All right, let's come back to this example. So the example here is, if this guy can go up. All right. So Unix, using the Unix system call called pipe, we are going to communicate between two processes. So how do you create this? How do you communicate between, say, two processes which have a parent-child relationship? Let's take a look at that. So the first thing that we are doing is we are initializing like a pipe file descriptor, which has two values of integer data type. Next, we are initiating this pipe system call pipe system call, and we are passing that pipe file descriptor as an argument to that. So what it'll return is, it'll return two descriptors, fd0 and fd1. One is going to be used for writing, and one is going to be used for reading. Actually, in the reverse order, fd0 is for reading, fd1 is for writing. So that pipe is going to return fd0 and fd1, one for reading and one for writing. And if you only have one process, this is going to create two file descriptors in that process. So right now we are saying in a parent, we had this system call, so we have a pipe to which we are communicating with a FIFO pipe buffer. So we are reading and writing to this FIFO pipe buffer. And supposedly, when we create a fork and we have a child, we are going to have the ability to read and write to that same pipe buffer. This is FIFO, so whatever goes in first, whatever we write first, is going to be able to be read first. Now, in your activity today, you will see a last in, first out. So you can imagine what is going to happen if you have that particular pipe buffer as a last in, first out. What are you going to get? Well, if you're communicating between two processes and you are putting things in, when whichever you put in last is being read first, you are going to have a scrambled message, right? Reverse message. But in this case, you get the message as in the same order as it was sent. All right, let's also talk about two file descriptors that are going to be standard file descriptors, say for a keyboard and a screen, a monitor. So file descriptor 0, not file descriptor parentheses 0. It's not an array element with 0. It is file descriptor 0 that is for standard input keyboard. And if you want to display something onto a screen, writing to a screen, then you would use the file descriptor of 1. Next. So what do we have in the parent? We are setting up one-way pipe from parent to a child. We have a few things that we are initializing: fork of an integer data type, value, child PID. And then, of course, we have the two file descriptors, pipe FD, pipe value. Then we have a 100 character buffer, and then we have n bytes of character data type. So all of these things we are going to use in our program to communicate between the parent and the child. So once we do that, let's try to see how we are going to set up the pipe before we fork. So we set up the pipe, and then we create the child, and then we communicate using that pipe that we created before the fork system call. So if pipe returns a value that is less than 0, then you know that there was not enough space in the main memory to initiate one more process, right? So you could not fork, you could not open that pipe. So in that case, you exit unsuccessfully. Return code for that is going to be -1. So this is first to check whether when you fork, are you able to fork or not? Do you have enough space in the main memory or not? Next. So you have set up the pipe, right? You have with this system call, you have set up the pipe, which looks like this right now. So you only have a parent. You have not used the system call fork. There's no child involved, and you have a FIFO pipe buffer through to which you are reading and writing. You're reading using FD0, and you're writing using pipe FD1. Right now, there's no communication going on because there's just a buffer and a parent process. Next. Oh, wait. Now, let's use fork system call so that we have this particular child that gets created. Both of them are going to have the exact same program. We are not replacing the program in the child here. We are not using exec system call. So fork, well, the return value of fork is stored in fork value. And you know that it is going to be different depending on whether you are in parent or child. And if you are in parent, the return value is going to be the process ID of the child. And in the child, the return value is going to be 0. Right? So that's what we know from the previous discussion. Now, in the child, you have the same two. Now, because the parent and the child are clone of each other, you have the same file descriptors, FD0 and FD1, that are in the child that the child can use to communicate with that same FIFO pipe buffer. So you have the parent that can read and write to the FIFO buffer. You have the child using the fork. We created the child, clone of the parent, that can also read and write to the same FIFO buffer. So here, this is set up so far as a two-way communication. But if you only are interested in one-way communication, then we can we can close certain ends of certain file descriptors. So suppose we say we only want parent to write, we don't want it to read. Then we can close this end out, right? We can close pipe FD0 in the parent. And then suppose we say we don't want our child to write, we only want it to read whatever the parent says. Then we can close out pipe FD1 in the child. That's what we are going to do. So over here, child closes the right end of the pipe. So I don't want my child to write to the buffer. I'm going to close out the FD1 pipe buffer in the child. Oh, by the way, how do I know it is the child? Right. So I've used else command here. I've entered the child, and I'm executing this particular statement in the child. Similar to what you guys might have done in the previous activity. The child says, my PID is whatever the get PID system call returns. So where is it showing? It is a printf command. Onto the screen, it is showing that. Right, so we are executing whatever is in the child right now. We printf the child process ID, then we close out the right end to the FIFO buffer in the child. Next, we are going to start reading because I'm setting up the child to read from the parent, setting up the parent to write to the FIFO buffer. So here I'm reading from the FIFO buffer using the system call read. What are you trying to read? I'm reading from the file descriptor 0, right, from right here, and I'm in the child. Where are you asking that message to be read to? Like, where do you want it to go? What is the message identifier? It is buffer, which has 100 characters. How much? What is the size of the, like, what length do you want to go over buffer? Size of buffer. So if you read, whatever you read, you are returning that value in n bytes. And if that is less than or equal to 0, that means that you were not able to read anything, right? The number of bytes that you read, if that is less than or equal to 0, then you didn't read anything. So there's a error message that prints out, child says could not read from the pipe. But if that value using read, if that is greater than 0, then you know that you were able to read something from the FIFO pipe buffer. And whatever you read goes in what? N bytes. Sorry, whatever you read goes in buffer. How much you read goes in n bytes. Whatever you read in buffer, suppose you want to display that onto the screen. What are you going to do? You're going to use the write system call. Where do you want to write? Standard output, file descriptor 1. right? We are not using FD1, we are using 1, which means that you're writing to the screen here. And the child says, this is what I read from the pipe, and 41 characters of what? Of buffer. So whatever you read from the FIFO buffer goes into buffer, right? 100 characters, you can put it there. And then you are essentially, whatever you get using the read command from the parent, you have not set that up yet. You are going to display that onto the screen and then exit out of the child successfully. So all of this is child's process. While this is going on, the parent is also doing something. Let's try to track that. Here you were checking for the fork value. Earlier it was 0, you did the child's business. Now you're checking for the else. Else, if it is not -1, if it is not 0, then it has to be the parent, something that was non-zero positive integer. Then you're printing, parent says my PID is so and so, whatever the get PID returns in the parent, and the child PID is going to be the return value of the fork. We know that right here, right? So if you fork in the parent, the fork value will be the child process ID. So child process ID is fork value, and you also print that up. So printf, parent says my child's PID is whatever the fork value that you have in that. Next, we still need to write. So before we write, we are closing out the read end of the pipe. So we earlier closed out the write end of the pipe from the child. Now we are closing out the read end of the pipe as far as the parent is concerned. Only one-way communication possible here, which is parent uses FD1 to write to the FIFO buffer, child uses FD0 to read from the FIFO buffer, which already we have written up. Next, we need to write to the FIFO buffer. How are you setting it up? Here, you're not writing to the FIFO buffer yet. You're writing to the screen now. You're writing to the screen. Parent says, this is what I wrote to the pipe. And 41 characters of this message, hello baby, exclamation point, new line character, which is 12 messages, 12 characters, right? So these are 41 ASCII characters here, 12 ASCII characters here. Spaces are getting counted as an ASCII character. New line is getting counted as an ASCII character. ASCII character has 8 bits, which is 1 byte. So 41 bytes equals 41 characters. So if you count these characters, there will be 41 there and then 12 over there. So parent puts out these 2 messages onto the screen, right? Next, it is going to write to the FIFO buffer now. To write to the FIFO buffer, it is going to use the file descriptor 1. What is it going to write? It is passing this message, hello baby, a new exclamation point. What is the size of that? 12 characters. So it wrote this particular message on the screen. It is, writing that same message to the child now, so that it reads it on its end and it displays that on the screen as well, right? So the child also, earlier, you see, child also says, this is what I read, and then it will write that on the buffer as well. Go ahead. 1 is the file descriptor as opposed to FD1. Yeah. For this standard output. Yeah. So suppose if you don't want to write to the FIFO buffer, you want to write to the screen, you use 1 instead of FD1. So over here, right, you see we are setting it up as if while you're running this, and you can try this out, right? Like you can make it into executable, run the executable, you will see this. 2 processes will be running, and they will be saying, this is the parent, this is the child. And then the child will say, this is what I read from the buffer, the message. Parent will say, this is what I sent to the child, the message. So it'll be displayed on the screen before communication, right? Before communication, it'll say parent will say this and this. It'll be written on the screen, and then it'll write this message onto the buffer, which the child will write onto the screen because it read from the same FIFO buffer, right? Because you see, it is writing buffer. What did this buffer? Whatever you read from the file descriptor 0. All right. Right. So parent writes to the FIFO buffer, and if it is not able to write, then you exit sorry, what is that? If, right. So if this is not 12 characters, which means that you are not able to write 12 characters, then you send print an error message, parent could not write, and then you exit successfully. Questions about this example? How you set up pipe first, then use fork. You've got a parent and a child, and then from the parent and the child, you can send messages to each other, or you can send messages to the standard output. And you can take messages in from the standard input as well. So you could actually change this up to, say, wait for the user to input the message, right, using the keyboard, standard, like using file descriptor 0. And whatever the user enters, you can treat that as, say, the parent's message, pass it to the child, and then display it on the screen. So you can do all of those like variations of this. All right, I think this is it. Forget about the activity part. I'm going to exit out of this as soon as it lets me. Close this out, and then let us start CPU scheduling. All right. So CPU scheduling, why do we need it? Lots of processes, limited number of resources. CPU cycles need to be budgeted, right? Like I need to say, all right, process one, you can run for this much amount of time. Then I'll have to assign the processor to somebody else. Then assign the processor to somebody else. So I need to make good decisions. Well, the CPU scheduler needs to make good decisions to how to make progress on all the processes that need the CPU's attention. There will be many. Who gets CPU? Is it going to be based on how much time they take to complete? Is it going to be based on how much time do they have left? Is it going to be based on their priority? Is it going to be based on something that is standard? Everybody gets the same amount of time in a round robin fashion. What is it going to be based on, right? So those are the ideas that we look at CPU scheduling in CPU scheduling. And as you may imagine, this is sort of one of the core, go away. All right. So CPU scheduling, that's one of the primary goals of an operating system, right? To schedule processes so that they can make progress. So what is the motivation? What's the goal of a scheduler? Different types of scheduling algorithms. We'll also look at the scheduling algorithms that are used very often. Those are, they rise to the top. Priority and round robin scheduling. And while we are doing all of these scheduling algorithms, we'll look at examples as well. Our goal will be what? Our goal will be to reduce the response time or waiting time, right? So in terms of time metrics, we would want to, on average, reduce it as much as possible. Recall the process diagram. For each process, a process gets admitted. No. Right. So it gets newly created. As soon as it gets newly created, it is in the job queue. Then it gets admitted to the ready queue. Ready queue means what? I am completely loaded in the main memory. I'm just waiting for the processor. So it gets admitted into the ready queue. From the ready queue, you can work on it. Well, when you work on it, the scheduler dispatch has to assign a CPU to it. Then it will be in the running state. From the running state, you may get an interrupt, it will go back to the ready state, or from the running state, you may be waiting for an event to happen or for some IO to complete, or you're waiting for some resource, right? Like some memory device or some IO. You're waiting, you have to wait. Then you go into the waiting state. Once the reason for the wait is removed, you go back to the ready state, and now you are again waiting for a CPU to be assigned. But from the running state, if you are able to complete the process, then you exit to the terminated state. So these are the stages a process will go through. And at each stage, you have to make good decisions in terms of who gets to run, who gets to finish first, right? So the CPU scheduler must make a decision at each of these transitions, because all the processes that are involved all the processes in the job queue are going through each of these stages. So we will be looking at what those good decisions versus bad decisions are going to look like for a CPU scheduler. So we are talking about this guy right here, CPU scheduler. Which process will go from the ready to the running, right? Which process gets the CPU when? Now, in order to talk about, hit this stop. All right. In order to talk about what is the outcome, we need to talk about some definitions because we will try to reduce these time metrics. What is the arrival time? Arrival time is defined as the time at which a process enters the ready queue. That's your arrival time. Got newly created, the time at which it gets admitted to the ready queue, called the arrival time for that process. Exit time, process completes its execution and terminates. So this is new to ready, and that is from running to terminated, right? So that's your exit time. Response time is the time a process spends in the ready queue to get the CPU for the first time. Not on average all the time, it is just for the first time. So it gets admitted to the ready queue, eventually has to wait until it gets the processor for the first time, then it goes into the running state. It may end up back in the ready queue, right, because of some interrupt or IO event to be completed. So that would be requesting the CPU for the second time, but that is not counted in the response time. Response time is only ready queue to get the CPU for the first time. How quickly was I able to get the CPU for the first time I needed it? Because a process will actually go through many cycles, right? So a process will have certain IO burst and some CPU burst. So a process will work, so it will use the CPU for certain duration of time, and then it will switch to some IO activity. Usually the process is spending short amount of time on the CPU, but longer durations for the IO activity. The wait times are bigger. So those are happening in bursts. What is a burst time? Burst time is total time taken for a process for its execution on the CPU. So all the time a process spends in the running state for the first time plus the second time plus all the times, all the time it is using the CPU resource is going to be in the burst time. Next, turnaround time. This is simply exit minus arrival. Exit time is when it completes. Arrival time is when it got into the ready queue. The difference between them is the turnaround time. That's sort of what we are trying to minimize, right? The total amount of time spent by a process coming from the ready state for the first time of its completion. So it comes to the ready state for the first time, gets completed when it eventually goes from the running state to the terminated state. The difference between those two times is your turnaround time. Or you can also look at it as exit time minus arrival time. Next, waiting time. Time it spends in the waiting state. Total time spent by the process in the ready state waiting for the CPU. So this is turnaround time minus burst time. Turnaround time is start to finish. Burst time is how much time the CPU was used. The difference between them is going to be how much time did you have to wait. Next, quantum time. Quantum time is, say, you are going in a round robin scheme, right? Quantum time slice, a particular time slice here to this, to this, to this, to this, back to the first one, right? So quantum time is essentially like a time slice for each process. And you need to do this sometimes to avoid process starvation. If processes are sort of fighting for resources, they are waiting for other resources, then you would have to sort of preempt them, make sure that they get an equal time slice of the CPU, and you remove them, you preempt them, stop them by force, which is sort of the ideology of round robin scheduling algorithm. We'll take a look at that. Let's see, throughput. Throughput is what? Number of processes that get completed in a given amount of time. So you're trying to increase throughput, you're trying to decrease waiting time, you're trying to decrease turnaround time. What are the goals of a CPU scheduler? We just said that, right? You want to maximize the CPU utilization. What does that mean? My CPU should not be idle. My CPU should be working on some process or the other, maximizing CPU utilization. Or it could be, the choices could be made in such a way that you maximize the number of processes that get completed per second. So this is maximizing throughput. Minimize average turnaround time, minimize average waiting time, or minimize the variation in the response times. Right? So these are some of the goals your scheduler, CPU scheduler, could have. So you're trying to make good choices to support these objectives. What is the basis for scheduling? The fact that processes alternate between bursts. The bursts are CPU burst and IO activity burst, or simply IO burst. What is a CPU burst? Duration of time CPU works on it. Then you switch to an IO burst. Then you come back to the CPU burst. So it'll be in bursts. The CPU burst duration are extensively measured. They have been documented. What we know is they vary greatly among processes in computers. They are invariably, they tend to have a particular pattern. And we'll take a look at that pattern on the next slide. In that particular slide, we'll take a look at the relative frequency of each burst duration. And it tends to have an exponential or hyper exponential distribution. Let's see. So CPU burst is the duration of time a process is using the CPU, right? But that, you can also think of that as, while it is using the CPU, it is eventually IO bound, right? So it works on the CPU, and then it becomes IO bound. So you call that a IO bound process. Now, a process that is actually going through some IO burst or IO activity, it is CPU bound, because it gets done with that, and it moves to the CPU. So the distribution, which has been extensively measured for CPU burst, this is only for CPU burst, looks like this. You have the frequency on the y-axis, which is essentially the number of CPU bursts, and the duration of each burst. And we can see that there are lots of processes that require burst duration of a very small value. There are lots of them. But as you go up in burst duration, there are very few processes that require a bigger burst duration. So many short bursts for IO bound programs. So they go through this CPU burst activity. Lots of, like every process will go through that, but each of them will get the CPU or need the CPU for a very short duration of time, because immediately after that, they will switch to IO activity. So those are IO bound programs. But if you look at the tail end of this distribution, you see that they are going to be fewer in frequency, fewer long bursts for processes that are CPU bound, meaning you had that IO activity happen, and now they are CPU bound. There are only going to be few of them for long bursts. So using this, we can design good scheduling algorithms because we now know the pattern. So based on some distribution of CPU bursts, we can use this to make better choices for our CPU algorithm, CPU scheduling algorithm. For example, if suppose you are thinking about a time slice, right? So try to give each one a time slice of maybe 3 milliseconds or 4 milliseconds, because you know that most of them will need that much. So something as simple as that could be a good scheduling algorithm based on some distribution that has been measured extensively, and it is invariably this same distribution, heavy tail distribution. Next, we'll take a look at these scheduling algorithms. Actually, this is not the complete list, but this is to start off with. First come, first serve, very obvious, right? Whoever comes first to the ready queue gets the CPU first. It is simple, but it is not very suitable for time sharing systems. And we'll take a look at some numerical examples why This is not good for time sharing systems because one process that comes in first actually could have a CPU burst of 100 milliseconds. Now, if you have a CPU burst of 100 milliseconds and the next guy needed the CPU for say 1 millisecond, that next guy, even though it needed the CPU at for just 1 millisecond, had to wait for 100 milliseconds, right? You starved second process for a lot longer than it may have been necessary. But if you preempted this process, all right, you have 100 milliseconds left, you're too long, process 2 just needs the CPU for 1 millisecond. Let me preempt process 1, maybe right away, or maybe after a small time slice, work on process 2, finish it, and then I'll come back to you, right? So that would have been better. But in first come, first serve, you cannot really do that because first serve is a non-preemptive. It is a non-preemptive. You guys understand about preemption, right? So preemption is I'm kicking you out. Like I'm not going to give you the CPU. Even if you have it right now, I'm going to snatch the CPU away from you. So the operating system, if it preempts a process, it is making a decision for the CPU scheduler to remove that process from the running state. So first come, first serve, a non-preemptive scheduling algorithm, because whoever comes first will get the CPU, they will complete, and then you go to the second process. So it's simple, but it's not really good for a time sharing system. Next, shortest job first, SJF. It performs well, but it is purely theoretical. Why is it purely theoretical? Because we are going to need to know which job takes how much time in advance. So it's a theoretical approach. But what we can do is we can use certain prediction for the burst time. So we can sort of predict how much time is a process going to take based on some history and some weighting of history, right? We can say, all right, let me make my prediction for how much time this process might need for a CPU burst. And my prediction, I can say, all right, let me base my prediction, half of my prediction will be based on what I predicted in the last time step, and half of my prediction will be based on what it was actually in the last time step, right? Half of the reality, half of the previous prediction, just as an example. And using those two values, I can actually predict a new value for the current time step. And I can use that, I don't know the real shortest job first, but I can use that to have a approximation of shortest job first. Again, we'll take a look at examples. Next, shortest time remaining. So remaining time, I know, right? I don't need to do any theoretical approach there. I know that. So there is a practical approximation to shortest job first, SRTF, shortest remaining time first. Now, how are you going to sort of compare these algorithms? Some time metric we are going to have to use. So what we will use is average waiting time as our metric. So first come, first serve. It is your simplest CPU scheduling algorithm. Nothing to do. You just link the PCB of the process that came in first to the head of the queue versus the tail of the queue. So you see this, request CPU first, get the CPU first. Come into the ready queue, you ask for the CPU first, you get it first. All the implementation is simply managed by a FIFO queue, which looks like this. So what do you have? You have a head of the FIFO queue, you have the tail of the FIFO queue. When a process enters into the ready queue, the process control block, which is what? All the information about the process. Process ID, process state, what the resources, accounting information. We looked at that in the previous lecture. All of the process related information is available in that particular process control block. It is linked to the tail of the queue. New process comes in, you get the PCB of that new process get links to the tail of the queue. And when the CPU is free, you assign that CPU to the process that is at the head of the queue. So as processes keep coming into this queue, everything that gets attached to the tail moves up in that first come, first serve basis. And if you are at the head of the queue, that indicates that of all the remaining processes, you were the first one who asked for the CPU. So whenever the CPU is free, the head of the queue gets the CPU resource. Questions so far? Pretty straightforward. Breeze. Yeah. So let's do this example. This will become even easier now. There are three processes, P1, P2, P3. They are in the ready queue. So they all arrived at the same time, for example. Let's assume this. Let's assume that P1 arrived first, P2 arrived next, P3 arrived the third. But they are all in the ready queue now. And their burst times are 24 milliseconds CPU resource I need, 3 milliseconds CPU burst, 3 milliseconds CPU burst. So P1, P2, P3 are asking for the CPU resource continuously for 24 milliseconds to complete, 3 milliseconds to complete, 3 milliseconds to complete. Because of the first come, first serve nature, P1 will get the CPU first. It'll use it, so waiting time is 0, right? For P, as soon as it came to the ready queue, it asked for the CPU, it got the CPU. So it didn't have to wait. Process 1 didn't have to wait. So its waiting time is 0, got the process, got the CPU, it completed at the 24 millisecond mark. For those 24 milliseconds, P2 had to wait. So its waiting time is 24 milliseconds. It got the processor next, it finished. Now it's P3's turn, but P3 had to wait for 27 milliseconds because of P1 and P2. But after 27 milliseconds, it got the processor. It needed it for 3 milliseconds. So after what? 30 milliseconds, all three processes were able to complete. So what is the average waiting time here? You just find the average of the three waiting times. You see that it will be 17 milliseconds. You can see that. So, and we want to minimize this waiting time, right? And we also want a scheduling algorithm that does not have a lot of variation in response times. We don't want it to be too different, even if we switch around the order of these processes. So let's take a look. What if we had a different order? What if P2 came first, P3 came second, and P1 came last? What would happen to the average waiting time? And we do this again the same way. Waiting time for P2 is 0, waiting time for P3 is 3, waiting time for P1 is 6 milliseconds. Try to find the average, and you will see that the 17 milliseconds of the waiting time, average waiting time, came down to 3. So it is not good for time sharing processes, but it is also not good for consistent low variation, right? Like you don't want too much variation in the response time. Sometimes it's big, sometimes it's small. That's not good because that doesn't allow the operating system to have a really good judgment about which process will need how much, right? So you want things to not have big variations in terms of response times. So this is well, this was, hold up. This was first come, first serve. But we also talked about first come, first serve in a different order. If the processes came in a different order, but also this is the shortest job first, right? So this is also the same example for shortest job first. Shortest job first, what do you have? P2 gets it first, P3 gets it second, P1 gets it last. So for the shortest job first, we have the same metrics. We have 3 milliseconds. But while doing this example, we also looked at the bad aspect in first come, first serve. You guys see that? So first come, first serve would not be too good because changing the order of these processes changed the waiting time significantly. But this example literally is for the shortest job first algorithm, which is theoretical, right? We would have to know ahead of time which process needed how much, what is the burst time for each process. You don't have that. You have the approximations for it, you have the predictions for it, but you don't know them exactly. So sure, we did better, a lot better than 17 milliseconds, but this is, again, theoretical. Questions about this? Maybe a better way to deliver this would have been to talk about first come, first serve, then shortest job first. No, maybe not. Maybe first come, first serve on the same side, stick with switching the processes. And then talk about shortest job first. But I kind of mixed the last two because they were the same. All right, let's move on to predicting burst times. So shortest job first, it is impossible to do because I need to know the CPU burst times for each process ahead of time, purely theoretical. So what is the approximation idea? Look at the history of the burst times. How much is process 1 using as a CPU burst as a history? What is it using? And what we'll do is we'll use this recent value and hope that the trend will continue. So our predicted value of the burst time is going to be some alpha times the previously measured value of the burst time and 1 minus alpha times the previous prediction value. So essentially you're saying alpha is a parameter that is controlling how much of that prediction is based on history, recent history, and how much of it is based on recent actual, right? Recent predicted versus recent actual. So initial value of this previous prediction is going to be a fixed default constant. So you're going to have to assume some previous prediction value, and then you can go through these predicted values. So suppose you say previous prediction was 1. Previous measured, well, you measured it, so you know that, and you have picked alpha based on how much you want to weigh each one. And then you will be able to calculate predicted value for the current time step, and then that will become the previous prediction for the next time step, and so on. Previously measured value, we will use t sub n minus 1. So this is for the n minus 1th time, and t for measured, actual. Tau for prediction, n minus 1th time, right? So still previous, n minus 1th time, but because it is prediction of the burst time, we will use tau to indicate previous prediction. And of course, the predicted value is going to be tau as well, but the time step for which it is being computed is n. So previous was n minus 1, the prediction was n. Or you could say this guy is say n, this guy is say n, and then this becomes n plus 1, right? The next one will become n plus 1, whatever that is. T is being used for actual things, and tau is being used for predicted things. Next, this is called exponential averaging. So what are we doing? We are using Tn as the actual length of nth CPU burst. So this is actual, which means that this is the measured one for T. Let's define tau n plus 1, predicted value for the n plus 1th CPU burst, for the next CPU burst. Alpha is a parameter that varies from 0 to 1. What we have for the prediction value, predicted value for the CPU burst time for the n plus 1th time is alpha times actual previous plus 1 minus alpha times predicted previous. So what are the edge cases here? Alpha is 0 and alpha is 1. So when alpha is 0, what can we say? Alpha is 0 means this goes out. Tau n plus 1 will equal tau n, right? What does that mean? My next predicted value is totally dependent on what I predicted earlier. Can I see that? My predicted value is the same as previously predicted. So essentially, I'm not using the actual measured value ever. So essentially, if I start off on a wrong step with that initial predicted value to be bad, I will continuously be bad, right? Like I have nothing of real data to support, to help my algorithm. So that's bad. The other edge case is what? So that's that, right? Recent history is not counting at all. New predicted is the same as previous predicted. So that's bad there. Alpha is 1 is your other edge case. When alpha is 1, your predicted value is totally dependent on the actual previous measured. It is not dependent on any of the previous predicted value at all. Over there, only the last actual CPU burst counts. Nothing before that will count because we are ignoring the previously predicted. All right, let's try to run these and let's try to track prediction versus actual. This is alpha is half. And tau 0, what is tau 0? Tau is for prediction, 0 is for initial, right? So that's your initial predicted value is 10. And in the black line, you have the actual CPU burst is the black line here, T sub I. And the blue line are the predictions. So right away, when you take a look at this, you see that the black line and the blue, well, the blue line, I should say blue line is kind of following the black line. Let's try to see how these are being computed. So for the first time step, what do? Well, you assume. Initial predicted value is 10. So there's nothing, no history to take a look at, no measured value to take a look at. So tau sub I for the first time step is 10. But what is it for the next one? Well, for the next one, right here, you're going to use half of the previously predicted and half of the previous measured. Well, half of the previous prediction is going to be 5, and half of the measured is going to be 3. So 5 plus 3, you got 8 right there. And you just keep doing that. Half of the predicted earlier, half of the measured previous. Keep doing that, and you will see that the blue line will more or less track the actual burst times, because you're using prediction history, something real, something predicted. So this is something that you can use to give you an idea about what is the burst times that this process is going to look for. And using that, you can go for the shortest job first algorithm, right? You can use that in the shortest job first, which is an approximated version of that is what shortest remaining time first does. Questions about this prediction? Go ahead. Just say assumed. So I have to start at some value. I could have been like wrong by a lot. So the actual value was 6. I guessed 10. I could have guessed 20, which essentially means that I would have taken longer to actually come down, right? So I would have needed a few more cycles to kind of come back to close to the black line. But we are looking at it not as an initial state. We are looking at it as a continuously running algorithm, right? It just keeps going. So it matters only for the initial catch up. After you catch up to the black line, then it doesn't matter. Yeah, arbitrarily chosen. All right, next, preemption and non-preemption. Preemption is, I'll kick you out. Non-preemption is, I'll not kick you out. I'll let you finish. So non-preemption is a new process can be dispatched only when a process terminates or switches to a waiting state. So only when the process gives up the CPU, then you can take that CPU and do something with it, something else with it. But unless the process terminates or unless the process switches to the waiting state, you will not be able to kick it out of the running state, preempt it. That's non-preemptive algorithm. Preemptive algorithm is a process, a running process may be preempted by another process based on some criteria. Took too much time, right? That's one criteria. So it's a little bit complex, and we'll take a look at some preemptive techniques as well. First come, first serve, non-preemptive. Shortest job first, non-preemptive. All right, let's see. Is shortest job first non-preemptive? So what if this happens, right? First come, first serve is this. You keep coming in, new processes keep going into this queue, and as soon as CPU gets free, you assign the CPU to the top of the queue, head of the queue. And then once the process gets it, it'll just use the entire CPU resource until it finishes. But in the shortest job first, go ahead. Right. So if the shortest job first is once you start, you're right. Let's see, I'm talking about like arrival times as well, right? Like you can have different arrival times for each process. Suppose we'll do an example later. It's going to be too complex to sort of explain it with words. Let's see, shortest remaining time first is a practical approximation to shortest job first scheduling. So here, when a new process arrives or a burst is complete, we are going to look at the remaining time estimates for each process, and whichever one has the shortest remaining time, we'll try to schedule that one for the CPU. So whoever has the shortest remaining time, I will assign that CPU resource to that process so that it can finish first. Let's see. Oh, when a process arrives or a burst is complete, right? So this is again non-preemptive. Example for shortest. Can you just go? All right. Example for shortest remaining time first algorithm. You have list of 4 processes in the left column. You have their arrival times in the second column. Right? This is the time that they are getting into the ready queue, and their estimated burst times are listed in the last column here. So let's see what happens. Process 1, right? At 0 milliseconds it comes in. It is going to ask for the CPU resource. P1 arrives, asked for the CPU resource, no competition, nobody else is there that is arrived. So P1 gets the CPU resource. It is going to work, sorry, it's going to make progress for 1 millisecond. What is going to happen at 1 millisecond? P2 arrives, right? Now you have got two processes, process 1 and process 2. Process 1, it already worked for 1 millisecond. So it has 7 milliseconds remaining. Process 2 came in at 1 millisecond. It has 4 milliseconds left. So at 1 millisecond, process 2 arrives with a time remaining of 4 milliseconds. Process 1 is 7 milliseconds. Process 1 will be preempted by P2. Next. You guys good so far? Next. P2 preempts P1. It gets the CPU resource, and you start making progress on process 2. But what happens at 2 milliseconds? At 2 milliseconds right here, P3 comes in. Well, its estimated burst time is 9. So we are going to ignore P3. P4 comes in at 3 milliseconds. Its estimated burst time is 5. So we're going to ignore that. We're going to continue working on P2 because it is in fact, the shortest remaining time first algorithm until we finish P2. You guys see that? So you will keep working on that from 1 to 5. So that's 4 milliseconds. You will work on P2. You will finish P2. Right? P3 arrived at 2 milliseconds. It has to wait because it is 9 milliseconds of remaining time. At 3 milliseconds, P4 arrived, but it has a time remaining of 5 milliseconds. So P4 waits. So P3 and P4 just need to wait until P2 finishes. But at 5 milliseconds, P2 finished. And I'm denoting that with a yellow down arrow here. P2 finished at 5 milliseconds. We will just do a quick budget of or quick list of how much we have for time remaining per process. P1, original 8, worked 1, 7 remains. P3, P4 both had to wait, so both of them have 9 and 5 respectively. 9 and 5. We didn't make any progress on P3 and P4. So which one are we going to pick? We are going to pick P4, right? So P4 starts. P4 starts, and well, there's no other process that is coming in. No need of preemption here. It is going to complete first. P4 will finish at 10 milliseconds. Then which one? P1, right? P1 is next. P1 gets it at 10 millisecond mark, and it'll work for 7 milliseconds from then on. 17 milliseconds, P1 will finish. And then the last one, P3 will start at 17 milliseconds, work for 9 milliseconds, and finish. At 26 milliseconds, P3 finishes. Questions about this example? You see how the arrival times sort of made it a little bit interesting at the beginning, but after that, once you finish the shortest job, really, you just had to pick the one that is remaining and work with that. Questions? Straightforward? Good. prediction to estimate that. Yep. So, and this is happening in real time, right? Like the operating systems in the background are running this prediction algorithm based on the history of the processes. And they're saying, all right, I know that Microsoft Word is using 10 milliseconds on average as the burst time. So I'm going to use that in my algorithm to decide when to give it the CPU burst. Go ahead. It is following the predictions very well, right? So if the real values are following the prediction values pretty closely, then operating systems are going to appear faster. But if you do some things that are pretty long, right, which you don't do usually, but sometimes, those are the times when you are going to experience some slow behavior, slow response times. Oh yeah, absolutely, absolutely. There are some even if you put the prediction by the side, right? Real operating systems, as much as they would want to keep that a secret, they have to use a few things. One, preemption has to be there. If you don't have preemption, they are doomed, right? Like there has to be some preemption because CPU needs to share between different processes. So preemption has to be there. Next, some amount of time slices also has to be there. Why? Because everybody needs some resource. You see, over here, P3 was 9 milliseconds, but because it was a pretty long job, it got pushed all the way to the end, right? And think about this. If continuously you get new processes that are requiring less than 9 milliseconds, P3 is never going to get that resource, right? So if that is the case, how are you going to fix that? Well, you fix that using aging. So what you do is, the longer you wait, the higher your priority will be. So using other techniques, operating systems will try to play more fair. Right. It is preemptive. So you see at the front, right? You kicked off P1. So shortest remaining time first is a preemptive algorithm. That's what I was trying to explain, and then I said, let's do this example. All right, let's see. Now, using that, we will try to draw Gantt charts. You guys are familiar with Gantt charts, right? For ID, you must have had to do like 355 of them. Here, the Gantt charts are already made for you. And as you can see, somebody has taken a lot of time trying to put these together. Believe it or not, this was therapy for me. When the time COVID started, that is exactly what I was spending my 10 p.m. to about 2 a.m. every night. I was trying to do this. Like, this was honestly therapy for me. I was just drawing things nicely, straight lines and color coding them. It worked really well. April 2020, here, this was my thing. Anyway, this is the same example, same processes, same time of arrival, same estimated burst times. So essentially the same example, except that now we are trying to draw two versions of the Gantt chart to to display in a table format, when did which processor complete, right? So over here, we have the timeline. P1 worked on it for the first millisecond, then 4 milliseconds for P2, 5 milliseconds for P4, 7 milliseconds for P1, and P3 finally from 17 milliseconds to 26 milliseconds for a total of 9 milliseconds. This can be written in a second version of Gantt chart, which is time versus process. So P1 for the first, P1 got it from 0 to 1. P2 got it from 1 to 5. P4 got it from 5 to 10. P1 got it from 10 to 17, and so on. So two versions of the Gantt charts are presented over here. And then using this, you can find out waiting times and turner. All the other time metrics can be evaluated using these Gantt charts. Next type of You guys are able to see that, right? Anyway, process scheduling, priority scheduling example. Same numbers, I think same numbers, yes, same numbers, but we have assigned priority. So we have an additional column of priority of each process at the right, and let's try to see what this priority scheduling algorithm does. Another example of a preemptive scheduling algorithm. So here, process 1 arrived first, got the CPU first, it worked on it for first 1 millisecond. Right? That's pretty straightforward right here. P1 arrives, starts, works on it for 1 millisecond. What happens then? Well, P2 arrives. Why is it important? Its priority is higher. Priority is higher is indicated by a lower priority number. So P2 is priority 2, so it preempts P1. Right? P2 arrives there, has a higher priority than P1. So P1 is preempted by P2 here. It works for 1 millisecond. Right, that is between 1 millisecond and 2 millisecond here, because at 2 milliseconds, P3 arrives with the highest priority. So P3 is going to preempt P2 at 2 milliseconds. It is going to get the processor resource, and it will work on it until for the total of 9 milliseconds, because it's the highest priority process. Next, in the meanwhile, at 3 milliseconds, P4 came in, but it had the lowest priority, so it had to wait. P3 finishes at 11 milliseconds. What is left? P2 is going to be assigned next because it is the next most prioritized process. It will work for how many? It originally worked for 1, 3 was remaining. So it worked for that 3 remaining milliseconds from 11 to 14. P1 gets it next because that's the next high priority process. We already worked for 1 millisecond at the beginning, 7 milliseconds left, which are assigned to the CPU from 14 to 21. The last one, lowest priority process, P4, that remains, we never gave it the processor. So 21 to 26, all of the 5 milliseconds are spent there. And again, exactly the same way as you draw Gantt charts for the previous example, we can draw Gantt charts right here. One of the versions is right there, right? Like this is one version of the Gantt chart. The other version of the Gantt chart is P1 from 0 to 1, P2 to 1 to 2, and so on. So that I think is shown on the next slide. All right, so that is one version of the Gantt chart, and that is the second one. So time and process. Process 1 gets it from 0 to 1. Process 2 gets it from 1 to 2. P3 gets CPU resource from 2 to 11, and so on. Good. This is for only one core. Yeah, absolutely. This is only for one core, but you can expand the same topic to multiple cores, right? Like over here, we are only talking about one core. But when you start looking at multiple cores, for each process, it doesn't really matter for a process, right? Okay, you're making progress or not. That's what matters for a process. So same calculations, but now the chances of a process getting the resource faster, sooner, is going to be high in that case. All right, next. Yeah, P3 finishes P2. Oh, yeah, we talked about that. So priority scheduling algorithm, preemptive, has the benefit of including priority of a process. Actually finishes. Is it guaranteed that it finishes the highest priority process first? So over here, you see the process is finished in P3, P2, P1, and P4, exactly in the same order as the priority. But is that guaranteed? No, it's not guaranteed, because just imagine P1, if it was priority 3, but if it had an estimated burst time of 1 millisecond, it would have already finished. Right? So it is not guaranteed, but most likely, yeah, it is going to follow the same order of priority. Not guaranteed, however. All right, let's move on to hidden dangers. And we sort of had that discussion already, which is indefinite postponement. So what if low priority tasks get indefinitely postponed? Because new processes start arriving with higher priority numbers, right? So if higher priority tasks keep coming in and you are following this priority scheduling algorithm, low priority tasks will keep getting postponed, right? They will keep getting pushed out, indefinite postponement, which means that we will not be able to make progress on those processes. What is the solution? Aging is a solution, which is to adjust the priority of a process depending on how much time it had to wait. So you wait longer, your priority numbers will be adjusted. Your numbers will be lowered, which means you will get a higher priority. So eventually they will become important enough to run. Questions about the solution here, aging and the problem of indefinite postponement. Right? Imagine this, like P1 is holding the resource up for 9 milliseconds, and then say P2, so suppose P4 is priority 4, right? And as P1, P2, as we are working on P3, P2, and P1, suppose new processes arrive with priority numbers of 1, 2, and 3. You will never want to work on P4, priority 4. So that's your indefinite postponement solution is aging. Next, round robin scheduling. Let us try to play fair, sort of a socialistic algorithm here. Everybody gets the same time slice, fixed time slice, called the time quantum. It is specifically designed for time sharing systems. Here you are making the ready queue circular. So you're going in a circle, work for P1 for 20 milliseconds, next 20 milliseconds, next 20 milliseconds, so on, and then come back in a circular queue. A process is preempted if it is still running at the end of the allotted time slice. So a time slice or a time quantum is a fixed amount of time every process gets the CPU. And because we have defined the time slice, you will never have an unbounded time, wait time for this. You will always have a bounded wait time for this. So imagine this. Imagine that there are 5 processes, right? P1, P2, P3, P4, P5. And each one gets 20 milliseconds. If each one gets 20 milliseconds of time, what is the highest time any process could wait for? Well, it could wait for P1 to finish, P2 to finish, P3 to finish, P4 to finish. But that's it, right? There are 5 processes, so you will get it after 80 milliseconds. You are bound to get it. Which means that if there are n processes in total, then the bounded wait time is going to be n minus 1 times the time slice for each one. Right? 4 times 20, that was total 5 minus 1 times 20. So the good news here is there is no indefinite postponement. Everybody will get the processor after the maximum wait time is say n minus 1 times the time slice for each process. So let's try to run an example here with a quantum of 20 milliseconds. This is round robin scheduling, and of course it is preemptive. After 20 milliseconds, if you need more time, you will be preempted. So there are 4 processes, their burst times are listed. P1, say P1 arrived first, P2 arrived second, P3 arrived third, P4 arrived last, but they all happened in that same order, but they all happened, say, between 0 and 1 milliseconds, right? So very close to the start of the algorithm here. So P1 gets it for 20 milliseconds, preempted. P2 gets it next. P2 doesn't need all of 20. P2 only needs 17 of it. So P2 will get 17 and it will finish. P2 gets to finish here, and then P3 gets the processor for the next 20 milliseconds. Then P4 for the next 20 milliseconds. It is a circular queue. So you come back to P1 for 20 milliseconds. P3, P4 now just left with what, 4 milliseconds. So P4 gets to finish there. And then you go back to P1 and it will finish there because you're less than 60. So you don't need more than, you need only 3 time slices. And then P3 finishes after that. sorry, P3 finishes after 2 time slices because there is still, you need to reach to 80. P3 finishes there. So everybody is getting the processor. There is bound time. There is preemption involved. So round robin scheme along with priority is sort of the scheduling algorithm which has the best features here. What if you pick a time slice that is too small or too big? What is the impact there? So instead of using 20 milliseconds, if you used 1 millisecond as the quantum time, what would happen? Right? So you're doing 1 millisecond, 1 millisecond, 1 millisecond, 1 millisecond. You're spending so much time doing switching between processors, right? Processes. So a lot of switching time, which is unnecessary. So it will make sure that there is equal processor sharing. However, it is going to be slow due to that switching overhead. And what you want is that time slice to be much larger than the context switch time. So if your context switch time is say 1 millisecond, you would want your quantum time to be much greater than that. In this case, it was 20 milliseconds. Because if it is comparable to the context switch time, then it's even worse, right? You are not even making progress there. You are just switching from one to the other. But what if the time slice was too big? So instead of 20 milliseconds, if it was 100 milliseconds, what would be the case? Well, in that case, it will go back to a first come, first serve scheduling algorithm, right? It will be as bad as that if the quantum is too big. All right. Next, what are you trying to get for the what is the trade-off between over here you have burst duration and the frequency. So this is the same exponential or hyper exponential distribution for burst times. The area of this part should be in such a way that it is greater than 80% of the total area. So using that metric, you can ensure that the resulting time is much greater than the context switch time. So what you choose for the time slice should be such a way that you get this particular area to be greater than your 80% of the total area. In other words, make your time slice much larger than the context switch time. All right. Don't do activity 22, but do an activity. Let me just take a look at the time here. All right. Okay, maybe we stop here. We'll stop here. You guys work on the activity slightly longer than usual, but nothing too difficult. You guys should be able to breeze through that. What's next? So on Monday, so we have an exam coming up next week. Thursday, we're going to have a comprehensive final exam. Again, it'll be the same deal as before. It will be offered in person, it will be offered online, so it's up to you guys wherever you want to be. I will be giving you guys the printed exam in the classroom, and I will be giving you guys the printed MIPS reference sheet. Let's see, people online, again, should have their cameras on, microphones on, open book, open notes, so you feel free to bring your laptops into the classroom to access the Piazza resources. So exactly the same way as we ran exam 1 and exam 2. You don't need to scan over here. I think that's an advantage to the people taking the exam in the room. What else? It's going to be comprehensive. I will be posting some back exam or list of topics, things that I do similar to before exam 1 and exam 2. I'll make up a section for final exam and I'll post some resources over there so that you have the material regarding that. We have one more lecture remaining. I plan to get to file systems. So we have deadlock and file systems. Those are the two topics. So let us see if we can finish that on Monday of next week. But no matter what, we will have all the topics on the final exam that we have covered. Go ahead. We can't. No, no. Yeah, that's unfortunate, but chaos. It's chaos. Yeah. Yeah, I need to figure out a good way of sort of bringing that content in. So, yeah, but then if I just post the resources and uh, do nothing about it, I can do this. I can point you to some really good resources on computer networking. There, of course, there are lots of material online, but there are some basic ones that are connected to a textbook that I would have ideally like to use. Some really good authors, Jim Kuros and Ross. Kuros and Ross, those are the famous names in computer networking. They actually had a connection with RPI. Kuros had a connection with RPI. Many years ago, he was, I think, a visiting professor at RPI. So they have a book on computer networking, which is currently in the 10th edition or 11th edition. So pretty good resources online. I'll point you to it, but unfortunately, I don't think it can be part of the course right now. All right, let us stop sharing. I will see you guys on Monday.